Thank you very much for the invitation to speak at this ScotMER Symposium. My name is Monica Fundingsland, and I have a strategic environmental and consenting role for offshore wind in Europe for Equinor. I will be talking to you today about the static fishing gear trials we have undertaken at our HyWIND Scotland floating offshore wind farm. Equinor has more than a decade experience with floating offshore wind. We have 2 floating offshore wind farms. HyWIND Scotland has been operating since 2017, and HyWIND Tampen in Norway became fully operational in 2023. Equinor has a research department, and we use our floating offshore wind sites to increase knowledge about the environmental impacts. Recognising that the marine environment is becoming an increasingly busy space, we collaborated with the Scottish Marine Directorate and Kirsty Wright, who is chairing this session, to test whether certain types of static gear can be used safely within a floating offshore wind farm. I'll be presenting the results of these trials today, but the full report and supporting video are also available from our website. HyWIND Scotland is located off the east coast, about 25 kilometres from Peterhead, in water depths from 95 to 120 metres. It has 5 6-megawatt turbines. We've used a steel spar substructure, and each turbine is attached to the seabed with 3 mooring lines and 3 suction anchors. The inter-array cables between the turbines are partly suspended in the water column. You can see them with the red dotted lines on the image. As many of you will be aware, fishing is not prohibited within offshore wind farms in the UK, but there's a perception that it's difficult to fish in a floating wind farm due to the underwater structures. So the primary aim of these trials was to test whether it is possible to fish safely with static fishing gear inside a floating offshore wind farm. And the fishing methods we tested were commercial fish traps, crab creels, and electronic jiggers. The secondary aim of these trials was to collect biodiversity data to increase the environmental knowledge of the area, and the trials also aimed to contribute to ScotMER evidence gaps on strategic fisheries management and coexistence between offshore renewables and commercial fishing. 4 trips were undertaken in the period of July to November 2022. Each trip was planned to last 5 days, but the first and last trips were impacted by adverse weather conditions. Equinor designated 3 fishing areas for these trials, based on a minimum distance of 200 metres to turbines and dynamic sections of the export and inter-array cables, and 50 metres away from all other subsea infrastructure, including mooring chains and anchors. We hired local fishing vessel Seagull and crew for these trials. Seagull is a 30-metre long ex-commercial whitefish trawler that now carries out guard duties for offshore wind farms. 2 types of triple parlour fish traps were used for these trials: commercial catch fish traps with a large mesh of 60 millimetres, and biodiversity fish traps with a small mesh of 20 millimetres, which are the same type as those used to survey inshore marine protected areas. The traps were fished in a fleet of 8 on branch lines 30 metres apart, and the trap types were alternated along each fleet. Fleets were weighted to avoid drift issues, and understanding the potential drift of the gear in this area was also part of the trial. Moving on to the results. The safe deployment and operation of the fishing gear was successfully demonstrated. There was no loss of fishing gear, no gear snagging, no gear damage, and no gear entanglement after leaving the gear to soak for 24 hours overnight. There were no issues with vessel handling, and no safety issues or concerns except adverse weather conditions, which played a major role in the decision of whether to enter the wind farm and deploy the gear. And gear drift was minimal due to appropriate weighting. The main aim of this trial, as I have said, was to test the safety of operating static gear, but just to summarise in terms of catch and viability, haddock and mackerel were among the most prominent species caught in the trial. Overall catch rates were low in relation to typical catch rates in more commercial creel fishing areas, but this was as expected, as there was limited commercial fishing activity in the Buchan Deep at the time the wind farm was constructed. And in terms of viability, all the static fishing methods are viable from a safety and practical point of view, but catch sizes were too low to be commercially viable. In terms of biodiversity data, it was difficult to compare fish catch inside and outside the wind farm due to difficulties identifying a control area which was similar in terms of sea depth and seabed type. And although these trials were not designed to look at fish aggregation around the turbines, there was some anecdotal evidence from the crew carrying out automatic jigging. They reported that there was more fish caught closer to the turbines than further away. The key findings of this trial is that firstly, with the right information and under the right conditions, it is possible to fish safely within the turbine area of a floating offshore wind farm with the static gear that we tested. Secondly, that the minimum distances to floating infrastructure used for these trials allowed the safe operation of the static gear and sufficient room to maneuver for a 30-meter fishing vessel. And thirdly, that weather and sea conditions are a key limiting factor to safe fishing inside a floating wind farm. Based on the experiences gained during these trials, we've recorded maximum wind speeds, tide speeds and wave heights as a guidance to operating limits for static fishing with a 30-meter vessel in the HyWIND site. These trials have been a long time in the making, but we're really pleased to have taken a first step towards improving the understanding of fishing within floating offshore wind farms, together with our partners in the Scottish Marine Directorate. Specific recommendations arising from this study includes that the location of all floating infrastructure should be made available to fishers in a format that can be easily uploaded to plotters, that defining minimum distances to floating offshore wind infrastructure is helpful to aid coexistence with static fisheries. These can then be uploaded and drawn on the ship's plotter so that the fishing vessel know their position relative to the infrastructure at all times. Also, that good communication between wind farm control centre and fishing vessels entering the wind farm greatly improves working relationships between the offshore wind and fishing industries, reduces risk of confusion and may provide a faster rescue response in case of an emergency situation. Finally, we're hoping to conduct similar trials at HyWIND Scotland and other floating offshore wind sites in the future, and these trials help inform how we can increase our knowledge and understanding through future research. Thank you very much.
Hello everyone, I'm Angela and I will present to you the OVAC project Fisheries Sensitivity Mapping and Displacement, FisMaDim. This project has as a goal to improve the methods to identify fishing activity at high spatial resolution, but also to assess the constraint and opportunity for the fishing industry, which means we are trying to do sensitivity mapping and also include displacement modeling. This idea is to provide maps at the end of the day, which provides evidence for the energy security strategy, but also 25 years environmental plan, Fisheries Act and others. The project is a 2-year project, which is more or less nearly done this summer. We are reaching the end of the project. Any further information on the project can be found on the web page of the project. The project is led by CIFAS, but are supported by University of St Andrews and the Scottish Government. We have in our project advisory group members of the industry, but also members from the policy side of things. So hopefully a nice representation. This work as a project per se has 3 work packages, apart from work package 1, which is project management 1. Work package 2 is looking into fishing location and to try to find new methods on fishing location. Work package 3 is sensitivity mapping and displacement. And work package 4 is trying to create a web tour for all of them. I will focus here on more practical ones, work package 2 and work package 3. As mentioned, work package 2 is looking more into the spatial distribution of fishing activity. In the first part, we did a review of the existing data method and tools. This is now published and can be found under this web link. We are also trying to find methods to improve the spatial representation of fishing activity. For this, we kind of looked into the data, and after the review, we figured out that the best way forward is to try to merge AIS data with VMS data. However, VMS data is only obligatory for vessels over 12 meters. So not every vessel which records fishing activity in the MMO fishing database has a VMS. Moreover, AIS data is actually from the Coast Guard, and it's more on health and safety requirement. So there's a device. This means that the AIS data and the VMS data doesn't share any kind of common identifier. The device of the AIS data can be moved between vessels, and therefore it's not easy to match them. We tried to match them, and we could find above 50% of the VMS vessels have also AIS data. However, only a small proportion of the MMO, also of the active vessels in the UK said, registered with MMO, have a VMS. So we have a small proportion of more fishing activity, which we could successfully integrate. As we would expect for some, if you're looking into the details, for some vessels, for some trips, adding EIS data, because it causes much more higher frequency, these signals are sent, we're adding more information. So in this aspect is great. However, we also see sometimes that actually it's the other way around, that VMS data, also there we only get every 2 hours information about the position of the vessel, while EIS is much more high frequency. Somehow the data is not there, the signals are not there. However, if we aggregate them all together, we can see that even with adding EIS data to the VMS data, we get much higher spatial resolution. From this aspect is what we are expecting, what we are hoping for. So this is an example for a static deer. We can do another example here as well for the pelagic trawl. And also here we see that we get much more information, much more detailed information on the fishing location, whether vessels were active. So after kind of improving the methods for at least a small part of the fishing fleet, we are now trying to get these maps into kind of constraint and opportunity maps. This is work package 3. Work package 3 is trying to identify insensitivity areas, so area of low or high conflict between fisheries and offshore wind farm, but also to include displacement. So we also have 4 case studies, displacement modeling upcoming, and then this all will be put together in an economic impact assessment for fishing. At the moment, the sensitivity mapping is a part which are in progress, which I will show you in a minute. So sensitivity assessment of fishing activities is rather, everyone understands something different about what is sensitivity. And to be sure that we, at least in the project, have a similar understanding or consensus on the understanding, we asked the member of the project advisory group to give us some keywords, what for them is sensitivity mapping. These keywords were then put into or analyzed by us, and then we saw that mostly economic dependency and vulnerability is the main keywords, main kind of topic, which always came out there as a high of importance for the project advisory group. Based on this, we tried then to find indicators who kind of measure or kind of measure these kind of terminology. Our indicators are mainly around business impacts, business concentration, but also something about irreplaceability of the area. So this is, for example, an example of the different indicators we are using. As baseline, we have landing values, and what we want to see is how much the kind of assessment of the area changes as soon as we're using a different indicator. And what we see here is, for example, landing values. We see some core areas of landing values where there's high landing values. However, as soon as we say if there's only a specific number of vessels or a high number of vessels with a significant amount of the annual revenues generated in the area, we see that much less areas become then significant or of high importance. And then we try to see if there's, for example, in this case, an indicator 1B, if there is a high value. So there's just a small amount of vessels with a high value of activity in it, then we would say that's a sensitive area. Similar to business concentration, we can do something similar. Again, we have baseline the landing values, and we want to see how much it changed as soon as we use it a different indicator. And here we're looking how many vessels are actually sharing the landing values in this area. And we see that also there is some areas here which have high landing values. It's also lots of vessels. So as soon as we control for it, for the number of vessels, then we see that actually it's of lower significance in this area, at least in this indicator. This change with indicator, each indicator captures something differently, something various. So we're ending up with about 12 different indicators, which are trying to capture different aspects of sensitivity. And we have 9 year groups, and we are using data from at minimum 5 years, but actually 10 years. So we need to all summarize it into a practical solution that we can actually use it for a policy for advice. This is what we are working on currently. And this everything of these ones will be then, all these maps we are generating will be available later on in the web tool, which is upcoming. But just that you have an idea, the web tool will look similar to what people may have seen on the Marine Scotland site already, an MPI, but also CFAS has a geofish side. So the idea is that we actually, yes, we're generating a web tool, but this web tool will be later generated in other web tools which can be publicly seen and so for publicly available for everyone. Thanks for your attention, and if you have any further questions, I'm pretty sure the project team would like to answer them. Thank you.
Hello, and thank you for inviting me to speak about the use of environmental DNA at the Blyth Demonstrator Wind Farm project. My name is Krystle Robson, and I lead the offshore team at Naturemetrics. Naturemetrics helps organisations around the world to measure, monitor and report biodiversity using DNA-based methods. We work with a range of different types of companies across many different sectors to inform environmental management strategies and to support conservation efforts. This could include things like surveying endangered species in remote rainforests through to conducting routine monitoring of marine biodiversity and feeding into environmental impact assessments. This project was in collaboration with Natural Power and EDF Renewables through the Offshore Wind Growth Partnership. We'll take a look at how eDNA monitoring compares with conventional fisheries surveys conducted within this area, and to determine at the end of this whether or not eDNA monitoring could be a candidate to support the expansion of the sector. We'll also explain a bit about eDNA for those of you who aren't familiar with the technology. So let's discuss some of the drivers that were the catalyst behind this project. I'm sure we're all aware that there's increasing pressure, both publicly and politically, on companies to minimise their environmental impact and effectively demonstrate this through robust environmental monitoring and, most importantly, reporting. Alongside the carbon mitigation targets, we're also seeing goals to ensure infrastructure projects have a net positive impact and secure biodiversity net gain. With this comes increased pressure on supply chain and the need for novel solutions that support achieving these goals. Scaling up conventional methodologies, typically used in the offshore environment, comes with a number of challenges. Firstly, they are time-consuming. Fisheries trawl surveys take time from the risk of being prevented due to health and safety, weather conditions. Expensive, as you need vessel time and specialised personnel both at the point of surveying and to analyse results afterwards. And data resolution. It is evident that new tools are needed to meet the challenges of biodiversity monitoring. DNA-based monitoring can provide scalable biodiversity data, and eDNA methods provide a non-invasive solution that can help to mitigate these challenges. Simply put, there's no actual need to physically catch or even see the fish to know that they are there. As promised, I'm going to provide a quick intro to environmental DNA, just for those of you who might not have come across it before. Things leave a trace of DNA in the environment. Fish will leave a trail of DNA in the water as they swim. So by collecting and filtering seawater, this allows us to capture that DNA, and this DNA can then be extracted in a laboratory and sequenced to identify unique genetic sequences. This is then compared to genetic reference databases to obtain a list of species detected within that sample. We can collect and extract DNA both from the terrestrial and aquatic environment. For this project, water samples were used to capture the DNA. However, DNA can also be extracted from sediment or soil samples. So when eDNA is collected from water, you pass the water, a few litres of it, through a filter like the one you can see on the bottom left of the screen there. And that filter traps the DNA, which we are then able to extract and amplify back in the labs to produce species lists of the organisms present, similar to this one. So the resulting data gathered is very comparable with conventional data sets and gives you a list of organisms present within the sample at the time of sampling. We are able to use different tests depending on the taxonomic groups of interest. So on this project, we were focusing on the fish communities. However, we can detect for everything from bacterial all the way through to marine mammals in the marine environment. So more specifically about the Blyth site. In 2021, ourselves, Natural Power and EDF Renewables were successful in securing funding via the Offshore Wind Growth Partnership Innovation Grant to conduct a comparison of DNA-based methods, trawling survey to gather fisheries ecology data. The purpose of the OWGP funding is to support projects that hope to demonstrate the ways in which new market-ready technologies could accelerate offshore wind site development and the overall expansion in the sector. So the overall aim was to identify whether or not using eDNA can support or replace traditional methods during the pre- and post-construction phases of offshore wind farm development. There's a lot of evidence already in literature about comparing eDNA with conventional methods. However, eDNA is still relatively new in the offshore space, so there's been very few studies where it's been investigated specifically in offshore wind infrastructure scenarios. An otter trawl was used and the net was towed for 30 minutes. At the beginning and end of each of these tows, 3 5-litre replica water samples for eDNA analysis were collected using a Niskin bottle. 4 surveys were conducted over 12 months, beginning in March 2022 and continuing each season and quarter, mirroring the typical compliance frequency for fish ecology monitoring. So, on to the results. eDNA recorded a total of 54 fish species, whereas the trawls identified 26. Both datasets recorded similar seasonal and spatial patterns. When comparing both datasets further, the variation in which species were detected highlights the strengths and weaknesses of each technique. eDNA was able to capture important species like the critically endangered European eel, marine mammals, and benthic species such as gobies, whereas the trawl data was able to capture elasmoprank species. To the original question of are new market-ready technologies such as eDNA able to play a part in accelerating offshore wind site development and the expansion? Well, eDNA collected 70% more species, utilised 40% less vessel time, and a third of the personnel time. So we are providing an efficiency there for both time and money, but eDNA does have its limitations. So to mitigate that, we use relative abundance as a proxy for population. It will still detect spawning and migration events. eDNA is brilliant for UK vertebrates, for greater number of species that are identified through it, and nature metrics are in the conversations with the regulators to standardise eDNA. In conclusion, the adoption of eDNA has the potential for huge benefits to industry by providing more efficient, affordable and scalable consenting and site survey solutions. This could speed up the development of offshore wind farms and reduce costs for the developers and operators, and hopefully reduce the overall cost of energy production. Regulator and stakeholder acceptance of eDNA methods for use in baselining for offshore development and monitoring will be a key step towards accelerating and improving environmental monitoring. The next sampling round is to include sediment samples in addition to the water samples to gather insights into the invertebrate communities within that sediment sample, and to continue to assess methodology and survey designs to keep improving efficiencies. Thank you for your time, and I look forward to answering any questions you may have in the upcoming Q&A. Thank you for your time, and I look forward to answering any questions you may have in the upcoming Q&A.